this is homework 2 solution session. In homework 2, we are given a 6-bit binary weighted capacitor deck with a segmented architecture by the attenuation capacitor of Cx, right? And we are requested to find the required Cx value for perfect linearity. Well, if ideal, we have no parasitic, and because we do not have termination capacitor, if this is 0, then Cx should be just a unit capacitor, right? But the problem said that we have 10% parasitic for both top and bottom plate, right? So when we are given Cx, the parasitic Cp1 will be, well, 7C here, right? So by them, we have 0.7 C parasitic. And because of this one, we have 0.1 XC by saying that Cx is X times of C, right? And the equivalent capacitance seen from the MSB side will be, well, Cx in parallel with all these capacitors, right? So we can write like this. Well, should we have Cx larger than unit C or smaller than unit C intuitively? Well, because we have parasitic capacitance here, because of the voltage attenuation or charge kind of leakage through this path, we're going to have reduced weights of these capacitors, right? So in order to compensate the reduced weight compared with the MSB part, right, we need to increase this Cx value. So we can say at least Cx should be larger than unit cap, right? How larger? Well, for perfect linearity, well, because this one is perfect linear and this one itself is perfect linear, so we need to just care these two guys' relationships, right? So, well, we can just take this one and this one. Well, if we say this one, the output voltage change by this capacitor is delta, then by this capacitor 4C should be delta over 2 for perfect linearity, right? So we just need to care that. So let's simplify the problem, okay, for this case and this case. For this one, well, we can just write like this. Because this part is common for this one and the remaining part, we can just eliminate because they will just change the denominator. Okay, so this one goes like this. And this part, when we change this B2 from 0 to Vref, right? Also this one from 0 to Vref. When this one changes from 0 to Vref, how can we describe this entire circuit? Well, we can utilize Thevenin equivalent circuit, right? So we have CEQ to this side. And what would be the open circuit voltage seen from this terminal by this one's change, right? So because this is open circuit, we just need to care voltage division by this network. So when V2 changes from 0 to Vref, the open circuit voltage will be what? Denominator will be the total capacitance, 7C and the parasitic. And we are changing this forces connection to Vref. This will be the VOC by B2, right? So what do I want to say? When B3 goes to Vref, we will have some voltage change here. When we change this one, the voltage appears here should be half of this case. So VDAC change by B2 should be half of VDAC change by B3. And VDAC change by B2 is what? We have all the capacitors, CEQ and C, on the denominator, and we are changing CEQ with its open circuit voltage, right? This should be half the VDAC by B3, right? VDAC by B3 is voltage division, right? And they give the signal will be VREF. So from this result, because we have a common denominator, we're gonna get this result. CEQ VOCB2, right? This cap and this charge, this cap and this voltage multiplication should be half of this cap and this voltage change. From this relationship, we can calculate CX like this. As we guessed from this CP, non-zero CP, CX is larger than unit capacitor. Okay. The second question is, well, just to use the capacitor value we have just found, but now the parasitic increases by twice. Okay, so the parasitic by this one will be 1.4 C, and by this one will be 0.2 multiplied by this capacitor value. So the total parasitic capacitance will be 1.62 C. Okay? And the equivalent capacitance seen from the MSB side will be just like this, right? So we have 0.988 C. Okay, now we are requested to find the worst DNL value. Okay, we know this one is perfectly linear and this one is perfectly linear. So what we care is what? The voltage change from this one to there. What I'm saying is that the code from 1110 to 0001. So the step size difference by this change will be 1 LSB. Right? We are just changing 1 LSB here. Right? So for this case, 0001 case, based on our earlier calculation, the equation shown here, right? What we need just to care is C VREF. This one will generate C VREF change. The normalized one, denominator is just ignored. Then the ideal voltage that should be generated by this 1110 should be what? Because this is 3-bit, right? Its maximum will be 7/8. When we think this one unity, C VREF, right? Then when we connect this one to 111 or VREF, then the output voltage should be like this. So one step difference, right? So when we connect this one to VREF, the ideal value is this much. Then what is the real value? Normalized, right? Eliminating the denominator, just like we did here and here, right? Then the voltage change, well, we have CEQ capacitor, right? And when we change this one, the voltage appears is CEQ multiplied by the entire capacity, 7C, which is connected to VREF, over the entire capacitance here, right? 7C is connected to VREF and entire capacitance is here, right? Just like this one here, right? That if we calculate, then we have this result. The ideal one is this one, which is 0.875 CPREF. We have this much, right? So from to here to there, I mean the one generated by this one to I mean the 0001 case, right? This one will have normalized value like this. So we can tell that the step size is 0.125 CVREF. It will be proportional to this value. So let's just eliminate CVREF because they are just common. Okay. So from the ideal condition, we have step size, one LSB step size of 0.125, right? But in real situation, we have this one earlier with the code 1110. And then when code changes to 001, we have again this one, right? So the step size in this case will be this one. This will be the maximum error step size. Okay, because each part is ideal. So when we change the code from LSB to MSB side, we're going to have the maximum error, right? Real step size, worst case step size, and this is ideal step size. So the error, step size error will be like this, while one LSB step size is like this. So DNL can be found one LSB over the error. So we have this much, 0.584 LSB error is the peak DNL.